This is just a short lecture on an inherent characteristic of supersonic flows, which are shock waves. I'm just going to go through this qualitatively rather than quantitatively, just so we get a sense of where and why shock waves form, what happens to the flow as they go through a shock wave, and then connect this in the last few slides to the idea of creating lift for supersonic vehicles. First of all, the Mach number. We define whether a flow is supersonic or not based on the Mach number M, sometimes written MA. Mach number is defined as this local convective speed, so this is the velocity of the fluid divided by the local speed of sound of the fluid. Often for an airplane, we'll define the Mach number of the airplane based on the speed of the airplane and the speed of sound of the ambient fluid through which the airplane is flying. Supersonic is the case where the Mach number is greater than 1. We'll see some key things happen when we reach this threshold. It changes drastically the airflow patterns around the plane. First key thing is this idea of the Mach angle. If we consider a plane here on the left, it's flying subsonically, and just consider there's on this airplane is some kind of beeper, something emitting a noise. And so if something's here stationary and emits a noise, the noise is broadcast out as a function of time in a ring that goes further and further away. But now we're at the idea that the plane is moving while it's broadcasting this noise at fixed intervals of time. And so the center of this larger circle is somewhere around here, and then the next circle's here, and then the next circle's here. So it's emitting these circles, but it's flying faster than, or slower than the sound wave can propagate. So it stays within these concentric circles. They're clustered or bunched to the left because the plane is flying to the left. As we approach this critical point, when the Mach number reaches 1, or sonic flight speed, we see this coalescence occur of these pressure waves that are being emitted at regular intervals because the plane is flying at the same speed as these pressure waves. Once we get to speed greater than Mach 1, it's now outrunning these emitted pressure waves. So we have the situation where here's the center of this circle, initial circle, and at some time later, the plane is here. So this is time A, and this is time B. And between time, or point A and B in space, between those two times, the plane has traveled a distance vt, and the sound wave has traveled away from this initial beep here at A, a distance A, t, where A is the speed of sound in the fluid. If we do some geometry, we'll see a front forms here. You can see there's a line that connects the tangency of all these concentric circles to the point that the plane is at right here. What is the angle that that line makes with the horizontal? Here it's alpha, typically we call it mu. What does the line makes with the horizontal? Well, this angle right here is a right angle. So we'll consider this angle right here. I want to compute this angle right here. And that angle is given by, well, the sine of that angle is the opposite over the hypotenuse. The length of these legs is AT. The length of this leg is AT. Let me write that in, say, purple. AT. And the length of this leg is velocity times time. Velocity of the plane times this time. So we have sine of mu is equal to A times T divided by VT. Therefore, mu, this angle, which is known as the Mach angle, is the arc sine. I'll just write A sine of A, and I'll cross my T's out, of A over V. But A over V is just the inverse of the Mach number. I'm going to run out of room here. I'm going to write as A sine of 1 over m. The arc sine of 1 over m. So we see a couple things. As you're flying faster, m is increasing. This angle gets tighter and tighter. So here, the angle is essentially 90 degrees. Here we're going faster. M is greater than 1, and the angle is is narrower. Now, let's think about a bluff body. This is zoomed. That was a pressure point. That was a point. And I guess a key note that I'll make and then erase is that anything moving in fluid, right? It's moving, and the flow's coming at it, and it has to go around it. What tells that flow to go around it? It's the pressure field. It's saying something's coming. We got to get out of the way. When you're going subsonically, the pressure field can stay ahead of the body, and it can say early on, get out of the way, flow out of the way. When you're going supersonically, the pressure field can't propagate upstream of the plane, and it has no way of saying get out of the way. Therefore, something must form. So here's our blunt body. Something must form to force this air from simply colliding with the vehicle. Very near the body in a bluff body, so it's kind of fat, as we're talking about a bluff body, we have what's called a normal shock wave. Right here, it's a perfectly normal shock wave. The flow moves through this shock wave. It goes from supersonic to subsonic. This says Mach less than 1 to subsonic. Some distance away from that normal point. So there's a perfect streamline that comes symmetrically in and actually stagnates right on the body right here. That streamline goes through a shock here, at which point the properties will change. We'll discuss that in the next slide, but the key one is that the Mach number drops to subsonic. Up here, we have an oblique shock. It's at an angle, and we'll discuss what that is in 2 slides. Through the oblique shock, the velocity goes through. The purpose of the oblique shock is to steer the air away from the body. Here it is. The body's getting in the way. Steer it away from the body. Behind an oblique shock, in most circumstances, not all, most circumstances, the Mach number will be greater than 1. It will stay supersonic, but it will be steered, and the Mach number will drop, but stay supersonic. Here they have a little boundary of where there is subsonic flow. It looks something like this. In that zone, everywhere in that zone, the flow is subsonic. Essentially, it's gone through this shock wave and these very steep oblique waves, and doing so becomes subsonic. Then as the flow, so supersonic, subsonic, turning, and we get here, so it's turning by regular pressure forces because it can propagate upstream of the bluff body in this subsonic region, and then it's going to expand through what's called an expansion wave we'll talk about in a few slides, and accelerate back up to supersonic speed around this bluff body. Very far away from the body, you have your traditional Mach angle, just like we do here. The body's in here somewhere. Far away, when you're looking from far away, all you really see are these Mach angle waves. Near the body, you have this more detailed flow field. Here, again, near the body, you have this more detailed flow field. Away from the body, the shock will tend to the Mach angle. And that is, again, the arc sine of 1 over the Mach number out here, as calculated out here, ahead of the body. So that's what the flow looks like near a bluff body. Now, the key thing, there's this region where you essentially have a normal shock. And normal shocks can occur under other circumstances. For example, flow through an engine or an improperly designed wind tunnel. And we'll talk about other places you have normal shocks. Normal shock, essentially you have the shock wave, you have flow on the left, you have flow on the right. This thing is very tiny. I think it's on the order, don't quote me here, something about 10 to the minus 5 meters, maybe smaller than that. So it's certainly sub-millimeter, way sub-millimeter scale. Very thin layer. And through that thin layer, the properties change drastically. So you have P1 and you have P2. And so you have P1 is greater than P2. Sticking with my 1 and my 2 properties, I have, oops, I have that backwards. Hang on a second here. If P2 is greater than P1, T2 is greater than T1, Rho 2 is greater than rho 1. You might recognize what kind of process would do this in a second. Mach 2 is less than Mach 1. U is in the velocity. 2 is less than U1. The entropy of 2 is greater than the entropy of 1. And now the key one we'll talk about more when we get into isentropic relations for compressible flow. But again, a stagnation point in any fluid, even right here, so there's a parcel of fluid right here to the left of the shock. If we bring that parcel of fluid to 0 speed isentropically, meaning we're no heating or cooling, and no friction is acting on that parcel. If we bring this parcel, which has a velocity, to 0 isentropically, the pressure it has at that point at 0 velocity is known as the stagnation pressure, or total pressure. We can do the same on this side of the shock. We can bring this parcel to 0 and get the stagnation pressure on this side, P02, P01, and we also have P02 is less than P01. Stagnation pressure is really a measure of work, useful work we can get out of the fluid. We've lost some work. What happened? We had a highly viscous, essentially an irreversible process. It happened in a very thin layer. What kind of process happened? It's a compression. Look at the pressure went up, the temperature went up, the density went up. It's a kind of compression that happens essentially instantaneously. Not quite instantaneously, but very close to instantaneously. This compression occurs. It's irreversible, and it is not isentropic. There's essentially a massive, you can think of a massive amount of frictional force that's happening here, or irreversible force. Stagnation pressure drops through the normal shock. Now we can compute what are these relationships, and they depend on basically resolving continuity, energy equation, and the momentum equation through the shock. And I'm not going to go into the details of that. You can certainly find it on the web. A key one is that all of them depend solely on the Mach number. If we look at particularly this one, Mach 2 and M1, the Mach number after the shock depends only on the upstream Mach number and nothing else. And this is for the normal shock only, for this perpendicular shock. M1 is always less than M2, and the larger I'm sorry, do I have this backwards here? M2 is always less than M1. And the larger our flow rate is, the higher Mach number on the left gives a smaller Mach number on the right. So if we're right at sonic speeds, essentially nothing happens. Your Mach number stays 1. And then if you go to 2, I'm not sure what it is offhand, but you get, say, 0.8 on the right. If we go to Mach 3, you might get to 0.7 on the right. So the higher Mach number on the left results in a lower subsonic Mach number on the right until you reach a limit, and that limit depends on thermodynamic properties of the fluid, in this case air. I don't recall the limit offhand, but it's something around 0.35. So as Mach number on the left goes to infinity, free stream, the Mach number on the right after the normal shock tends to some asymptotic value, and I'm not sure what it is, 0.3 something is the number. What about if we don't have a bluff body? You can have something what's called an oblique shock. So again, let's just pretend for a moment this is some kind of missile, right? That has a wedge angle like this. So again, it's moving supersonically. Apologies, it's difficult to see this. It's moving supersonically, and we don't have the ability to project ahead and say, well, look out, flow, there's a wedge coming. You need to skirt sideways. So what forms, depending on the circumstances, we'll look at those in the next slide, it can be in an oblique shock that looks something like this. Oblique shocks are different than normal shocks because they occurred in an angle relative to the free stream flow. That's the oblique part of the oblique shock. To solve for the oblique shock, you have to consider a few things. One is that the flow has to be deflected by this angle theta. That's the point of the shock. And the other is that the flow, that you can take the flow coming in here, and we can look at the component that's normal to the shock and the component that's tangent to the shock. The component that's tangent to the shock is essentially not operated on by the shock, and nothing happens to it. the component that is normal to the shock, and the amount is normal depends on the angle of the oblique shock. The component that's normal is operated on just as in the normal shock relations. So with knowing the normal shock relations and knowing theta, you can go through a bunch of math and figure out what these oblique shocks look like. Essentially, what is this angle here, which we will call beta, where theta is the physical angle of the missile, or half angle, I should say, of the missile. You put that together, again, the flow is supersonic, otherwise we wouldn't have this. And you get what's called a theta-beta Mach diagram. Now, I haven't looked at these in a while, but I will try to go through it. The idea is you have a certain wedge angle, and you have a certain Mach number. Let me try to trace one in, say, orange. Let's pick 2. How's that sound? Mach number 2 is this curve right here, where the 2 is. Now I'm going to take this wedge angle. This is a missile physical geometrical wedge angle, or a wing wedge angle. And we say, what is the oblique shock angle for that wedge? Now we take the wedge up and we move it till it intersects the Mach line, Mach 2. That's the free stream Mach number, and we see, what is it? It's about 45 degrees. So if we have a 15 degree wedge and we're flying Mach 2, our Mach angle, the angle of the oblique shock will be about 45 degrees. But then you might notice, wait a minute, there's another solution up here where it intersects up here, the same Mach line, and the result there is much higher. It's about 82 degrees, almost a normal shock. This family of curves, so each deflection angle, each geometric angle for a given Mach number has 2 solutions. Those solutions are divided in this diagram by this red line here, where it says theta equals theta max. The bottom, it's labeled. The bottom ones are called weak shock. The top is what we refer to as a strong shock. Strong shocks always have a Mach number behind them that is less than 1. Weak shocks generally have a Mach number behind them that is greater than 1. They do not cause the flow to become subsonic. What we're seeing here is there's 2 possible solutions. Nature prefers the weak shock solution, the lower angle and with supersonic flow behind. So when in doubt, use the weak shock solution. The other thing you'll notice is that for a given deflection angle, oops, hang on, how do I get rid of that? Okay, sorry. For a given angle, actually, let's do it the other way. Let's say for a given Mach number, you can do it either way. A given Mach number, we'll stick with 2, which is the orange line, Mach 2. Now we increase our deflection angle. So we're making a missile that goes from a narrow missile to a thicker missile to a thicker missile. So we're increasing the wedge angle. As we move to the right, you can see for a given Mach number, so we start here and we're increasing our missile angle. What's happening is our shock wave angle is increasing. So here it might be something like this, and then it gets wider, and then it gets wider. But there's a critical point. At some point, now I'm at deflection angle 22 and a half. And if I go up here, I realize I'm right here. Now let's go all the way to 25. 25 does not intersect the Mach 2 curve. There's no solution here. And what that means is that there is no oblique shock for that case. And let me go back to sketch for you, if I can, what that would look like. So again, if this angle, what angle was that? 25 degrees and Mach 2. So if this was equal to Mach 2, and if this wedge here equals 25 degrees, we see there's no solution for an oblique shock. And what we have is a normal shock near the body. The oblique shock cannot be strong enough to turn the flow. That's basically what happens. And the shock wave looks essentially like, oh, that's badly drawn. Try again. It's a normal shock here, standing off from the body, and then it turns to an oblique shock. It's not perfect, but I have to do. So you get a normal shock off the body under those circumstances. So again, there's 2 solutions. And generally speaking, for a deflection angle, there's 2 solutions of the oblique Mach angle. Pick the weak solution, which is the smaller one, which results essentially in supersonic flow behind it. There's, for any Mach number, there's a critical deflection angle above which you can't have the oblique shock. You have a normal shock off the body, because the oblique shock, it gets steeper and steeper, and at some point it just can't turn the flow anymore. Finally, I should note, there is a little zone here, which is between the blue and red line, where you have subsonic flow behind a weak shock, and that happens right before you hit that critical angle. So as we were increasing the deflection angle, we found the oblique shock was getting steeper and steeper, and eventually it's still an oblique shock attached to the nose of the body, but it's producing subsonic flow behind it. And then if we increase the wedge angle anymore, the shock has to come off the body. You can also play the same game by picking a wedge angle and modifying the Mach number, and you'll get a similar thing that happens. So these oblique shocks and normal shocks steer flow around supersonic bodies, depending upon if they're bluff or if they're streamlined, depending what the Mach number is. But this is for steering flow away from a body. We also have a situation where, what if flow is moving along a body and then the body sort of expands like this? We could think of a flow through a wind tunnel, through an expansion section of a wind tunnel. In this case, the flow needs to be able to figure out how to turn this corner. Again, it is supersonic flow. So information about this corner coming can't propagate upstream. So we have the opposite, essentially, shocks, which is called a Prandtl-Meyer expansion, except this can be a frictionless process. That's different than a shock. These are essentially an infinite number, these little expansion fan waves, and their purpose is to turn the flow like this. In this case, you see the Mach number increasing, and we will have the pressure P2 decreasing through this expansion. We will have the density decreasing. And the entropy stays the same. Other than that, they're the opposite of the normal shock. The density decreases, pressure decreases, temperature decreases, Mach number increases, velocity increases, entropy stays the same. Let's have a look at what this looks like. This is what's called a diamond airfoil. It's moving supersonically. This is visualized using probably a Schlieren system, essentially because you have drastic, rapid changes to the density. Then you put light through it, just like on a hot day where you see you're looking at a car and there's heat coming off a car, the hood of your car, for example. You'll see the sort of waves as the light is being refracted through the varying density. This is the same thing, a Schlieren system. How is that spelled? I think it's spelled like that. Were used to visualize presence of shocks and supersonic flow in a wind tunnel. And so here's a wedge. It's at pretty close to zero angle of attack. I can't quite tell, but let's pretend it's at zero angle of attack. So you have on the nose here, it's a wedge, right? So you have these oblique shock waves. And then it moves up over the top, and now we have a convexity. It's the same situation as this, sort of, as if it were like this. So you have an expansion that occurs here, essentially like low pressure going over the top of the airfoil, and then we have shock waves on the back as we move back to free stream pressure. So this is P atmospheric, and so the parcel comes in, it's shocked to higher pressure, expands to lower pressure, shock back to atmospheric pressure. The process going through this. Associated with these shocks are drag. Also associated with the shock can be lift. Here's a diamond airfoil. Well, this one's clearly at an angle of attack relative to the supersonic incident flow. And so you have a wedge here, but the wedge is at an angle relative to this. So the top surface is actually it's drawn here to be horizontal. It doesn't have to be that way, but it's drawn to be parallel or very close to the free stream flow, which results in an oblique shock of a relatively at an angle that's not very steep. And below that, we have what's effectively a steeper wedge to the flow, resulting in a steeper oblique angle. So again, if I measure the obliquity relative to this horizontal line, Here's 1, here's 2. This would be beta upper, and this would be beta lower. Beta lower is greater than beta upper, which means that the Mach number behind on the underside of the foil is going to be smaller than the Mach number up here, because they're moving through different shocks. This one's more close to a normal shock. This is an oblique shock. So we could still even have supersonic flow up here, possibly, and probably. And here we have subsonic flow, depending upon the specifics. But a key difference is behind this stronger shock, the pressure is higher. So we have atmospheric out here. Here we have P2. Here you have, it's getting to be a mess. Here you have P2. Here you have P1. And P2 is greater than P1. It went through a stronger shock, which means that the pressure down here is greater than the pressure up here. And net force due to pressure is going to be lift in the Y and the Z direction, the up direction. And then you still have your expansions and your shocks in the back, but it's this asymmetry between the top and the bottom that drives this pressure difference. It comes completely from these shocks. Well, a key component, I should say, comes from these shocks. So the nature of the airfoil is you don't need this specially shaped fat airfoil to shape the flow and get it to accelerate. Here it's all about generating shocks, and a very thin airfoil will do as long as it's structurally sound. You can generate significant lift and supersonic flow with a super thin airfoil. You don't necessarily need any kind of fancy shape. Of course, you have to be able to fly at low speeds to get to high speeds. That's another issue. That's all I want to say. I'm going to put up, I have one more thing to say. I'll just write here. I'm going to put up a calculator. I'll put it on the main page and also on this week's homework. I happened to see it tonight when I was looking around. And they seem to have an iPhone page version as well, or I should say a tablet phone page. Anyway, it's a little calculator, allows you for normal shocks and oblique shocks and other things to punch in some numbers. For example, for the oblique shock, you can put in your Mach number and your shock angle, and it will calculate a bunch of stuff that happens through the shock. It's sort of a useful tool because, taking these shocks, we just take conservation of energy, momentum, and mass. We can come up with what are the shock jump relations, what are the jumps in these properties across the shocks. But they're sort of messy formulas, so what that web page does is do the calculations for you.